Hello everyone, we are FAU Ocean Engineering Senior Design Group 3 and we were tasked with the development of an ASV that is capable of self-docking and self-anchoring. So our team was comprised of 7 members, namely myself, Declan DiPietro, Amadeo Ibarro, Tobia Llorenz, Abigail Lockard, Brendan Palamasio, Griffin Farmer, and Daniel Young. Our team was also split into groups that would handle the mechanical, electrical, and software aspects of this project. So the goal of this project was to create a self-anchoring and self-docking ASV, which can minimize the necessity of on-site personnel presence, thus decreasing the cost of operation. To fulfill the project objectives, we had to create an autonomous surface vehicle that was capable of starting off from a docked position, releasing itself from the dock, traveling to a predetermined GPS location that was at least 50 meters away, deploying its anchor, remain anchored for 15 minutes, retrieve the anchor, navigate back to the docking station, and then reattach itself to the docking station at the end of the mission. In addition to the project goals and objectives, it was also required that the ASV be autonomous and have RC capabilities as a backup, as well as being able to log all health and location data during the mission. To the right of the screen, you can see the ASV in action as it goes through its various states of the mission, which were release, navigation, anchoring, return, and docking. Here you can see how our design progressed from its conceptual design state to the final prototype. The vessel was 5 feet in length, had a beam or width of 30 inches, and had a maximum attainable speed of 1.43 meters per second. The vehicle structure consisted of twin hulls with inlaid aluminum deck rails. Aluminum strut channels, which served as cross members, were then mounted to the deck rails. These strut channels acted as a mounting base for the various electronic and anchoring components. The docking system was comprised of 2 stern-mounted electromagnets, which, when activated, would attach the vessel to the docking plate, which was affixed to the floating dock. This design also utilized a dual-spring gimbal system, which helped regulate the influence of external forces on the system, such as wind and tide, while in the docked position. The anchoring system consisted of a hurricane boat anchor, an anchor guide, as well as a Lumar CRW 400 windlass. The electronics box housed the battery as well as the PCB. Mounted on top of the box was a Garmin 19X GPS. The box was also fit with multiple Maxicon and Minicon connectors to allow for waterproof routing of cables in and out of the box. The PCB was engineered to connect all the necessary peripherals to the Raspberry Pi Model 4B single-board computer. The Pi was set up with the Linux-based Raspberry Pi operating system, which allowed for the mission code to be programmed using the C language and also to utilize the Wiring Pi open source library for general-purpose input-output control. The mission code was broken down into 8 different states to handle various aspects of the mission. In addition to these 8 states, a kill state and a remote control override state were also added for safety. Moving on to the construction of the vessel, the holes were precision cut out of foam using a CNC mill. The aluminum deck rails were then inlaid and the holes were fiberglassed over. They were then faired, sanded, primed, and painted. Once the PCB was finalized, it was installed into the electronics box and all external connectors were soldered. Components such as the electromagnet assembly, the anchoring assembly, and the GPS and compass assemblies were then attached to the boat. Once assembled, the vessel had a total weight of 93 pounds. Here you can see a view of the ASV fully assembled sitting in the water connected to the docking station. Final testing was conducted in Whiskey Creek behind the CTEC campus. The ASV traveled 67 meters from its starting location, successfully deployed its anchor for 15 minutes, retrieved its anchor, returned to the docking station, and then successfully executed the docking maneuver and attached itself back to the floating dock. In the end, the ASV was able to successfully fulfill all of its mission requirements. In addition to this, the team was able to fulfill all of its objectives roughly 3 weeks ahead of schedule. Here is a short animated overview of our system. Here the vessel can be seen disengaging its electromagnets, releasing from the floating dock, and starting its mission. The ASV then enters the navigation state as it traverses from the floating dock to its anchoring location. The graph on the left shows heading versus the distance to the anchoring location. The ASV is able to navigate autonomously using a series of waypoints generated between its starting position and its final position. As the vessel approaches its anchoring location, it will then automatically switch into the anchoring state, where it will first apply a short burst of reverse thrust and deploy its anchor. Once the anchor is deployed and has hit the bottom, the ASV will then wait for a specified period of time to align with the current. Once aligned, it will then reverse and let out enough line for a 2-to-1 anchoring scope. The graph on the left shows the distance from the anchoring location versus the time in seconds. The ASV then sits at idle until it is time to retrieve its anchor. Once the anchor is retrieved, the ASV will then turn around and set its heading back towards the docking station. Once properly oriented, it'll re-enter the navigation state and head back towards the dock. Once within a specified distance from the docking station, the ASV will then execute a 180-degree turn, activate its electromagnets, and back into the docking station. On the left is a polar plot that compares heading to distance to the docking station. The ASV is now docked.